Determine the Laplace inverse of s squared plus 9s plus 2 over s minus 1 squared times s plus 3. So we're going to apply a partial fraction decomposition on this expression. So let me copy it down here. We have s squared plus 9s plus 2 over, and then I have s minus 1 squared times s plus 3. And so when we split this up, we notice that we have a repeated factor s minus 1. So we would definitely start off with s minus 1 for our partial fraction decomposition, but that's not enough because this is a repeated factor, so we will also have to include all the higher powers of this factor as a fraction. So we have s minus 1, s minus 1 squared, and if this was a cubed, then we would also have plus 1 or plus over s minus 1 cubed. So that's the first part. And then let me write down the coefficients in the numerator, and let's denote those by a and b. And then we have one more factor, s plus 3. And since that is not a repeated factor, we can write s plus 3 in our denominator of the next fraction, and I'll call that coefficient c. Now, in order to figure out what a, b, and c are, we're going to multiply both sides times the denominator here on the left. So I'm going to take this expression on the right, and I'm going to multiply it by s minus 1 squared times s plus 3. And I will do that on the left-hand side as well. And what I get then is, so s minus 1 squared times s plus 3. And on the left-hand side, the denominator disappears, so I'm left with just s squared plus 9s plus 2. And on the right-hand side, when I multiply this out and I divide out an s minus 1, my first term becomes a times s minus 1 times s plus 3. And then my second term, the s minus 1 squared will cancel out here. And so I'm left with b times s plus 3. Right, the s minus 1 squared cancels with the s minus 1 squared here. And then my final term will be plus c times s minus 1 squared. Because the s plus 3 and the s plus 3 cancels out. Now, at this point, there's several approaches that you could take. So one approach would be to FOIL this out, distribute the A, the B, the C, and then combine like terms, and then see, since this has to hold for all S, we then can compare the coefficients in front of the S squared, in front of the S, and just the constant coefficients, and see what needs to be equal to 0. But again, this needs to hold for all S's. So this holds for all S's. And so what we can do is we can make some smart choices for S. So here's a smart choice. So smart choices. The first smart choice would be S equals 1. And why is that? Well, if I plug in S equals 1, this term becomes 0. That means A cancels out. And when I plug in 1 here, the C cancels out, and I'm just left with my coefficient B. So if I plug in 1, I get 1 squared plus 9 times 1 plus 2 equals, and then I'm going to just write 0, right? Because if I plug in 1 here, I get 1 minus 1, and that's 0. And then plus B times B times 1 plus 3. That's my S. And then plugging in S equals 1 makes that 0. So that last term is again 0. Evaluating this gives me 12 equals 4B. And so my final answer for B is divide both sides by 4, and I get B equals 3. So we have 1 out of 3 coefficients. So another smart choice for S would be S equals -3. Because if we pick S equals -3, then this becomes 0, this becomes 0, and we only have an equation for C. So I have -3 squared plus 9 times -3 plus 2. It's what I get when I plug it in on the left-hand side. And then that is equal to, plugging in -3 makes that first term 0, makes that second term 0, and then the last term is C times -3 minus 1 squared. And so plugging that in and evaluating that leads to, on the left-hand side, I get 9 minus 27 plus 2. So that gives me negative 16. And on the right-hand side, negative 4 squared gives me positive 16. So that's 16c. And from that, it follows that c equals negative 1. Now, at this point, we've run out of smart choices for S, in terms of like things completely canceling out. So what we do then, instead of still multiplying this out, we'll pick any value of S that is convenient. So we're now going to do a convenient choice for S. And usually, if that hasn't been an option just yet, S equals 0 is a convenient choice. So if we plug in S equals 0, then we get 0 squared plus 9 times 0 plus 2. Right, 0 squared plus 9 times 0 plus 2 equals, and now we plug in 0 here. So that is A times 0 minus 1, and then 0 plus 3. And then plus B times 0 plus 3, and then plus C times 0 minus 1 squared. Okay, now let's simplify this. On the left hand side, we just keep 2, and then we get A times negative 1 times 3, so that gives us negative 3A. And then here we get 3 times B plus 3 times B. And then finally, negative 1 squared gives you positive 1. So finally, we have plus C. Now, we already know B and C, and so at any time you could have plugged those in. We know that B is 3, C is negative 1. So this simplifies to 2 equals negative 3A plus 3 times 3 plus negative 1. And when you solve that for A, what you'll get is that A is equal to 2. And so we've done the hard part here. We've rewritten this expression here, and we use the partial fraction decomposition we just needed to find these three coefficients. So to find the inverse Laplace transform now, so we're trying to find the Laplace inverse of s squared plus 9s plus 2 over s minus 1 squared times s plus 3. We split that up into the Laplace inverse of a over s minus 1, and we found that a is 2, and then plus b over s minus 1 squared, and b was equal to 3, and then plus c, which is -1 over s plus 3. And then by linearity, this is equal to 2 times the Laplace inverse of 1 over s minus 1 plus 3 times the Laplace inverse of 1 over s minus 1 squared, and then minus the Laplace transform of 1 over s plus 3. These are pretty straightforward. Those are the Laplace transforms of e to the power at. So that first one, that first part will be 2 times e to the power 1t. And for the last term, this one right here, we get minus, and then e to the power -3t. Now, this Laplace inverse needs a little bit more work here. So if you look it up in the Laplace transform, we know that the Laplace transform of t to the power n e to the power at is given by n factorial over s minus a to the power n plus 1. So the inverse Laplace of this expression is equal to this. So we need to compare this expression here with our expression over here. And s minus 1, compare that with s minus a. We see that a is equal to 1. And then compare n plus 1 with 2. So that means that n equals 1. So in other words, and you also see that the 1 factorial matches up here, so we don't have to multiply by any kind of fraction to make that work. So the Laplace inverse of this part right here will give us t to the power n, so that's t to the power 1, and then e to the power at, with a being 1, that's e to the power t. And then the coefficient in front of that is a plus 3. And that is our final answer to this inverse Laplace problem.